My name is Merlec. I'm a Ph.D. candidate student in computer science and engineering from Korea University. In this presentation, I will be presenting about my Ph.D. Thesis topic, which is a smart contract-enabled dynamic consent management scheme for GDPR compliance. This thesis was supervised by Professor O. Peter In from Korea University in the Department of Computer Science and Engineering. The presentation will cover the following 5 points, as you can see in the screen. Recently, sensitive personal data is being massively collected and used by corporations, scientists, and government in their daily activities. This has led to unprecedented challenges to personal privacy rights and data securities. We have experienced many cases with the COVID-19 pandemics in many countries where personal data has been used for mass surveillance and censorship purposes. This is because our existing consent management systems are not adequate for complying with data protection and privacy regulations such as GDPR to systematically empower users to provide customized consent management their personal information and be able to control who can collect, access, and use their data for specific purpose and specific periods. User also should be able to delegate their consent rights and access to the consent-related information, as well as withdraw the given consent at any time. Dynamic consent management is a novel approach to involve people in the usage of their personal information. It attempts to solve the limitations of paper-based and static consent systems, which provide the users with fewer options and less flexibilities to define and manage their consent preferences. Aims to give back the user control over their data and allow them to dynamically manage their consent on the data utilization. For such systems, transparency, accountability, security, and privacy should be ensured. However, these features are challenging to be achieved with conventional CMSs that rely on trusted third parties, where ICTs are required to comply with a legal and regulatory requirement for consent agreement and enabling customized interfaces for user interaction. As you can notice, these CMSs have the potential to unlock economic benefits and create new business opportunities by addressing intersector, cross-border, and large-scale data sharing challenges. Flexible and dynamic approaches are required to achieve specific, informed, and engaged consent agreements for legal personal data usage with guarantee of transparency, security, and privacy. Few solutions exist that allow user to systematically manage their consent on their data. That user should be able to delegate consent rights, access to the consent-related information, and withdraw previously given consent at any time. However, most of existing solutions are domain-specific and centralized systems that lack essential features such as trusted data provenance, transparency, and accountability. Therefore, in this study, we aim at designing a dynamic consent management system using smart contract for GDPR-compliant personal data usage. To achieve this goal, the following design requirements have to be achieved, from where we can derive subsequent research questions. First, who are the key stakeholders and what are their legitimate role and responsibility? Second, how to systematically enable data subject to control their personal data collection and usage consent under GDPR throughout the data cycle. 3. How can individual consents and rights be explicitly and systematically expressed in human and machine-readable formats? How to give data subjects access to their personal data collection and usage activities. 5. How to notify data subject and report regulator about consent agreement violation. Finally, what should be done when the consent agreement clause are violated or when the purpose for which a consent was collected is not longer valid. To address these issues, we proposed a smart contract-based dynamic consent management system powered by blockchain technology for GDPR-compliant personal data collection and usage. It's a user-centric approach that leverages smart contracts to give back user control over their consent on the personal data collection and usage throughout the data lifecycle, where consent right can be delegated and audited by users by tracking the log event on the blockchain. Users get notified about any consent agreement clause violation and can withdraw the related consent at any time. We also design a GDPR consent compliance verification model. To protect user privacy, decentralized identifier, verifiable credential schemes have been proposed and built using W3C standard. The IDs are used for user profile identification, authentication, and authorization, while for credentials are used for consent agreement, credential proof, authentication, and verification. Next, we integrated IPFS nodes with a system to store data off-chain in a decentralized and reliable way. Transaction history and access log are recorded on the blockchain to enforce trust and provide tamper-proof data provenance, accountability, and traceability. We also proposed an extended base access control scheme for the proposed IPFS-based secure decentralized data storage system. Finally, we designed and built a prototype of our system on Quorum blockchain platform to show its feasibility. We assess the system security and privacy, and the system performance also is evaluated in terms of algorithm complexity, transaction throughput and latency, block propagation time, and storage network bandwidth consumption. I will compare our work with the related study in the literature. As you can see in this table, we compare our work with existing is considering several such as the legal basis, the user-centric approach which we use, DID, verifiable credential, the ability to grant consent and delegate consent, to audit the consent related history, withdraw consent, the privacy and security analysis, the blockchain related features, the use of IPFS, and so forth. We can argue that this work is different from the study in the literature, as it focused on the design and implementation of a dynamic consent management solution using smart contract to achieve specific, inform, and engage consent agreement for legal use of personal data based on GDPR, wherein accountability, transparency, privacy, and security are granted. We adopted a permission consortium blockchain network to meet the requirement of our system. Good security, confidential, and privacy preserving interaction and data exchange among several stakeholders from different organizations. On the proposed system design, identified 4 major stakeholders with their respective role, which are described as follows. Data subject refers to an identifiable person whose data is collected and used. Data controller is the one providing features to manage the personal data and is the one deciding why and how the personal data will be processed. Data processor is a third party that processes personal data on behalf of a data controller. Finally, the supervisory authority or regulator is the one in charge of regulating and controlling the data protection regulations, compliance, and resolve conflict. Each participant has a set of rights and obligations to be fulfilled. A valid consent should be freely given, specific, informed, and unambiguous. For underage or minors, their legal guardian should consent on their behalf. Subjects are given the right regarding changing or withdrawing consent at any time. The consent concepts are defined in the figure below, where a consent is granted by a data subject to a person or a delegation on a specific data at a specific time for a specific period in a specific context. A consent agreement results in a consent agreement contract that has a status that can be valid or invalid throughout the data cycle, from the creation to the destruction of data. The figure provides an overview of the proposed dynamic consent management system. It includes 5 main use cases, starting from 1 and 2 that correspond to the user profile creation and role approval. 3 and 4 steps correspond to the consent request and agreement. 5, 6, and 7 correspond to the data access request and authorization by the data processor. And 8 correspond to the access by the data subject to audit the status of the granted consent and activities history. And finally, 9 is the case corresponding to the consent withdrawal by the data subject. For modularity purposes, our system is divided into 4 layers from top down. The personal data layer is the layer that provides data management related features, and the dynamic consent management layer is the middleware layer that feature all the functionalities related to the dynamic consent management. And the distributed ledger technology and secure storage layer is the layer that provides the blockchain related functionalities and the secure decentralized data storage based on IPFS protocol. And finally, the secure communication infrastructure is the one providing secure communication for secure messaging. Participant user must sign up for a membership user profile and get authorized before joining the network and using the system. User profile may be assigned one or multiple roles. The membership user profile creation, role requests, and approval procedure is illustrated in the figure 16. Data is assumed to be encrypted before being stored on S and published on blockchain. The personal data set verifiable credential schema defined in JavaScript object notation for linked data is provided in the listing 6, composed of 4 sections. The header section that comprises verifiable credential attributes, and the second section is the part is the data set related claim. Section is the authentication section that includes the signature signed by the data subject for ownership verification. And finally, we have the proof section, which is issued by the data controller upon approving the publication of the dataset on the blockchain and issue the verifiable credential, which will be used a consent agreement. Agreement and action rights model is defined using JSON profile for XACMail. XACMail is a noisy standard that describes both policy language and access control decision request and response language XML. As we can illustrate in the listing 7, a consent agreement verifiable credential schema coded in JSON for linked data. This schema is divided in 4 main sections. The first section contains the consent agreement verifiable credential header related attributes. The second section contains the consent agreement claim, which in all the consent agreement related specifications such as participant, resource, context, constraint, operation, and status. And the next is the consent agreement claim authentication that contain and claim authentication related parameters. Finally, we have the consent agreement verifiable credential proof that is issued by the consent agreement verifiable credential issuer. 5 steps are performed from consent agreement claim creation to verifiable credential issuance on blockchain. First and second phase correspond to the consent request and consent agreement claim registration. You can see in this figure, and agreement provide all the consent related specification information that are sent to the data subject to give the agreement. When the agreement is given, consent agreement contract is created on the blockchain. The next phases are related to the consent agreement claim authentication parameters creation, the proof creation, and verifiable credential issuance on the blockchain. Agreement claim authentication parameters are created by the data subject in order to be able to verify and authenticate the ownership by signing the digital signature containing the hash of the claim with the private key that will be verified using the corresponding public key. Credential proof creation is set by the data controller after verifying all the requirements such as data protection impact assessment and privacy protection impact assessment as required GDPR. After the proof, they can issue the verifiable credential on the blockchain to be used later processor to demonstrate that they've collected genuine consent agreement from the data subject. Moreover, our system provides a mechanism for data subject to be able to withdraw a given consent anytime. For example, when the reason for which a consent was collected is not longer valid, or when consent agreement clause is violated, subject can decide to withdraw or revoke a given consent by using the following mechanism. First, they have to test the consent agreement withdrawal that need to be approved and executed by the data controller as shown in the figure. The algorithm describe in detail all the steps required for withdrawing a consent. Also proposed an extended role-based access control management scheme of the IPFS-based secure decentralized data storage system for the proposed system. The proposed extended role-based access control system is integrated with a key management module and decryption engine, which is used to encrypt the data before storing them in the IPFS and decrypting the data in order to be accessed by the user. In the figure 22, we highlight the Quorum and smart contract design for permission and role-based access control, where we have extended by adding an extended role-based access control, which is mapped with the permission interface smart contract and the permissions implementation smart contract. So proposed GDPR consent compliance verification scheme enable data subject to assess the available necessary protection mechanism to ensure that personal data security and privacy are ensured by conducting data protection impact assessment and privacy impact assessment as required by GDPR. First of all, they have to figure out whether the personal data is involved or not. If yes, they have to check whether the consent is required or not. And then they have to verify the user role. The data processor has to collect the consent from the data subject. And then the data controller will verify whether the data protection impact assessment has been performed or not. If yes, they have to check whether the privacy impact assessment has been satisfied or not. And finally, they check whether all the GDPR compliance related requirements are satisfied. Finally, they check if the user is authorized to perform such operation. If all the conditions are satisfied, they can authorize the processor to perform the processing on the personal data. So far, I've described all the main functionalities of the proposed system. So now I will elaborate on the system implementation and provide some evaluation results. Quorum was used to implement our system. Quorum is an Ethereum-based permission blockchain platform with advanced enterprise-grade functionalities that enable contract and transaction privacy with pledgeable consensus protocol and scalable performance. We use several programming and scripting languages: Python, XAML, JSON, JavaScript, and a bunch of APIs such as REST API. Smart contracts were developed in Solidity programming language. Decentralized applications were implemented using Python and Flask, which is a micro web framework for Python. Test and validate our concepts. The system-related infrastructure was deployed on premise in a Docker container environment. We use Docker composed configuration files to generate a consortium blockchain network, as illustrated in the figure on the left, where deploy 7 nodes with the associated transaction manager and logger server. They were deployed on the top of Docker engine, which is installed on the Ubuntu server. So the table in the middle provide all the detail related to the deployed content. So we deploy a maximum of 25 containers, including the tools we use to monitor and manage our infrastructure, as well as the IPFS nodes. The table 6 provide all the experimental environment setup. Cakeshop IDE was used to explore, monitor, and manage all the resources of our consortium blockchain network. As you can see in the figure, the IPFS based storage network, we use the IPFS GUI dashboard to monitor the status of our IPFS nodes and the related peer nodes of the worldwide decentralized storage network, as you can see in the figure 25. Now, let me elaborate on the system evaluation. Our privacy and security analysis has revealed that our system is secure and privacy preserving, as it relies upon and extends advanced features of the underlying Quorum permission blockchain platform. The implemented smart contract code was successfully analyzed and verified using highly precise verification tool for Solidity smart contract. It has revealed that they are secure against well-known vulnerabilities up to date. As Quorum blockchain provides support for Byzantine and crash-tolerant consensus, our network is guaranteed to be available even in presence of adversary nodes. The personal data, confidentiality, authenticity, and integrity are guaranteed on-chain via the blockchain, which has all transaction data hashed and timestamped. Off-chain data are secured using encryption and decryption techniques based on elliptic curve digital signature algorithm. To preserve user privacy, we use DID for user profile identification, authentication, and verification, while verifiable credentials are used for consent agreement, credential proof, authentication, and verification. Our analysis has revealed that the features of our proposed solution fulfill all the requirements we have defined earlier in terms of key stakeholders and role identification. Second, the user-centric dynamic consent management approach that was described earlier, and the consent and right expression in a human and machine readable formats. I've extensively explained about that part. And four, we have the consent and data usage activity history accessibility, which is accessible through the blockchain for traceability and accountability purpose. And five, the consent violation notification. I mentioned earlier the system provides support for a consent agreement violation to be reported to the user automatically using smart contract. And last but not the least, the consent agreement withdrawal. So the user can definitely be able to withdraw any given consent when needed. As you can notice, this solution enables data controller to easily perform data protection impact assessment and privacy impact assessment and document them before performing any data processing activity for legal compliance under GDPR. The performance of our system was assessed in terms of smart contract algorithm complexity, transaction throughput and latency, block propagation time, and storage network bandwidth utilization. The experiments were conducted to investigate how the transaction workload variation could affect the system performance using two main consensus algorithms that include RAFT and IPFS consensus protocol. To understand the impact of input transaction submission rate variation on transaction throughput and latency, in our experiment, we generated a variable workloads ranging from 10 to 2,500 transactions per second input transaction rate to stress test our system. We focus on write transaction workloads instead of read operation that do not of the ledger. Experiment was repeated 3 rounds. Then we calculated the average transaction throughput value and latency. The space and computational complexity of our proposed algorithm were assessed to determine the efficiency in terms of smart contract code space, creation and deployment cost, and computational complexity. The table 7 provides the space complexity of 8 main smart contracts with the related creation and deployment gas costs. While in the table 8, we provide the measurement of main transactions that interact with the blockchain in terms of writing and reading operation complexity. We have also analyzed the transaction throughput and latency of our blockchain network. By transaction throughput, we mean the number of transactions processed per second by the blockchain network, while the transaction latency is the time elapsed between the transaction submission and the response reception time. In the figure, we analyze the impact of input transaction submission rate on the transaction throughput. For both Raft and IPFS consensus protocol, they have shown that the transaction throughputs scale linearly for low transaction input rates until it reaches a saturation point for 800 for IPFS and almost 1000 for Raft consensus protocol. In the figure 27, we analyze the transaction latency variation based on the transaction input variation. Notice both Raft and IPFS consensus protocol shown that the transaction latency increased linearly as the input transaction submission rate is increased. However, Raft consensus protocol has performed better compared to IPFS consensus protocol. Our experiments, we also evaluated the block propagation latency. As Quorum support fault-tolerant consensus protocols such as Raft and IPFS, the block creation and validation are guaranteed as the network can still operate and reach consensus even in the presence of adversary nodes. With Raft consensus, block are minted on demand no more frequently than every 15 milliseconds. Raft has a fast block time and does not create unnecessary empty block, whereas IPFS has a regular interval during which the blocks are created by a validator, and it creates continuously even empty block which waste resources. Table 9 provides the DID registration, transaction, and block-related space and time complexity measurement. And in Table 10, we provide consent agreement, transaction, and block-related space and time complexity. In the figure 28, we analyze the impact of input transaction submission rate on the block propagation time for two main transactions, DID registration and consent agreement registration. As you can notice, both transactions are scaling linearly. However, DID registration transaction has shown low block propagation latencies compared to consent agreement registration related latency. This is because consent agreement related latency is more complex and has more read and write operations. Finally, we have analyzed the impact of our input transaction load variation on the storage network bandwidth utilization. As you can notice in a figure 28, our system required less than 0.4 megabit per second of bandwidth consumption to keep working in the most efficiently way. This results in high transaction throughput and latency, as I've discussed in the previous slide. However, there are still few potential limitations and challenges that need to be resolved. As the system is complex, we need efficient and user-friendly key management scheme to take the advantage of the advanced security and privacy features proposed by our system. The smart contract and blockchain Oracle issues so need to be taken in consideration while designing smart contracts and integrating them with decentralized application. The GDPR and blockchain immutability nature. So in some cases, withdrawing consent under GDPR may require deleting stored data for user to exercise the right to be forgotten. These are still challenging issues when it comes to the blockchain technology due to its immutability nature. The smart contract vulnerability also is a big issue that needs to be regarded. The smart contract adaptability and applicability need also further research. Finally, we need some method to automate the GDPR compliance checking and security and privacy policy verification. As a conclusion, I can say in this study, we propose a user-centric dynamic consent management system that leverages a smart contract for GDPR-compliant personal data utilization. It allows users to systematically achieve explicit and informed and engaged consent agreement on different type of personal data and control when and how the consented data can be collected, accessed, and used. It also enables data controllers to conduct data protection impact assessment and privacy impact assessments and document them before any data processing activities is performed under GDPR. We also proposed a secure decentralized storage system powered by IPFS protocol, which is integrated with our system, where blockchain is used to promote trust among participants and record immutability, transaction history of consented data collection, access, and utilization. This guarantees trusted data provenance, security, and accountability. We also proposed an extended role-based access control system using smart contract for IPFS-based secure decentralized data storage, where user can delegate the consent rights and audit them by tracking events recorded on the blockchain. Preserve user privacy. DID and verifiable credential schemes were designed and built based on W3 standard. Finally, a GDPR compliance verification model has been designed for the proposed scheme. Most importantly, this study provides a valuable theoretical and practical background for future research to be conducted. Future research direction to be investigated includes considering cluster or cloud computing platform to deploy our solution and conduct in-depth performance and scalability analysis for variable number of nodes and batch size. The development of novel, efficient, and user-friendly key management approaches merit further investigation. The development of an automated compliance checking engine for GDPR and security and privacy policy verification, and the development of auditable and privacy preserving compliance-proof verification techniques for consent revocation that require personal data deletion by the data subject. These remain open questions that need to be addressed in the future. Thank you very much for taking your time to follow my presentation.